Okay. So we just have a little bit in 6-1 to finish up. We're still in fractions. We're going to be in fractions for a little bit. So let me start off. By asking you guys a question. Let's see. This one is crazy nice. Which is bigger? And we kind of talked about this before, but I want to kind of overlap last time before we start off here. This kind of relates to a question somebody asked earlier. Which one is bigger, obviously? 6-7. It's crazy, right? So it's sort of like 4 chairs versus 6 chairs. The whole idea of LCD is really just like terms. So these are like terms, so I can compare them very easily. And 4/7 versus 6/7. Obviously, this guy's more. Does anyone remember the, just to kind of verify this a different way, does anyone remember how I can, if the fractions were worse, does anyone remember how to check to see if they're equal or which one's bigger? Yes, if I cross multiply. So if I had these two, just to verify our answer. You gotta be really careful how you do this. 7 times 4, and 7 times 6. However you put the symbol in the middle. If those numbers are equal, the original fractions are equal. If the first dude is smaller, the original fraction, first fraction is smaller. It's kind of almost too nice to believe. So that's one of the last things we talked about last time is why is that true? You guys that all with me? Now on this problem, I didn't need that, but I just want to show you, you get the same answer. Thank the gods. If we didn't get the same answer, we'd have to throw that out because it wouldn't get us the right answer, so it's a bunch of crap. Okay. So what if I make this a little more interesting? What about which one of these is bigger? Without doing it this way, without using this.
5/11.
Yeah, why is 5/11 bigger?
So bigger pieces.
Bigger pieces, how do you know?
Because there's less.
Less of them, so I didn't make as many cuts, right? So the first piece, I'm dividing 5. So if you look at it computationally, how do I make a fraction get smaller? I make the bottom bigger. If I divide by more, my answer is getting smaller. So you can look at it computationally and realize in the second fraction, 4 little 5 is being divided by 17. Holy shit, that's going to be much smaller than 5 divided by 11. The other way to look at it is like brownies. If you have a big chunk of brownie, you cut up into 11 parts, those brownies are going to be bigger than if you cut it up into 17 parts. So if you got 5 brownies out of the 11 tray, and somebody else got 5 brownies out of the 17 cut tray, their brownie is going to be smaller. You're going to get less total brownie. Yes? You're probably like me. You want to maximize your brownie. Okay. So this one will definitely be bigger. So if the bottoms are the same, the comparison is easy. If the tops are the same, the comparison is easy. Now, of course, what gets worse, and the reason we have this other way of doing things, is if the bottoms and the tops are both different. That's when things get bad. So like if I had 11/17 versus 13/20. So what would you do here? Cross multiply, exactly, right? So 20 times 11, does anyone know, what's 20 times 10? What's 20 times 1? So what's 20 times 11? 220. 17 times 13, oh shit. 17 times 10 is 170. 17 times 3, 51, so you get 221. Holy shit, I didn't even mean to make it that close. So which one, let me take these out now. Get away. How would I write the inequality between the two fractions?
11/17 is less than.
Oh shit, I wanna do that, go on. Yeah, 11/7, so the way you would write it here is the same way you write it here. So that would be my answer. I made a better problem than I thought I was gonna make. Sorry, I didn't try, it just came out. Okay. You guys kinda with me? So it's kinda cool. The little cross multiplication thing, if you think about it, this was easy because they have the same denominator. So one way to do these problems is to make a common denominator. Make a common denominator. I just want to show you can actually say it. What would the LCD be for these two? How would you get the LCD for those two? Here's the great thing. All LCD is LCM, and when the two things are relatively prime, they each need each other. Does that make sense? So, if I had 3/5 and 1/15, what's the LCD? 15. Because 5 goes into 15. Can 5 become 15? Yes. So why is the LCD of those two not 5 times 15? Because 5 and 15 are not relatively prime. 15 has a 5 in it. In fact, if you break 15 down, you can see exactly what the other dude needs to become the same thing. Are these two relatively prime? Be really careful. Are they prime? Are each of them prime?
One is.
Good, one is. Are they relatively prime? They could both be not prime, but are they relatively prime? Yes, because 17 and 20 do not share any factors, correct?
Yeah.
So this guy would need a 20. You have to multiply this guy by 20, you have to multiply this guy by 17. But isn't that what we do when we cross multiply? So that's why the cross multiplication thing works. It is exactly like finding a common denominator. Maybe. That's why that process works. It's almost too good to believe. Yes?
Can you cross multiply with 3 fractions?
No. So you can only officially directly cross multiply when you have one fraction and another fraction.
Like, but cross multiply, like, to find the common denominator.
You can find the common denominator between 3 fractions, but there's no way you can. The cross multiplication doesn't make any sense when you have 3 fractions. Yeah. You could take 2 at a time and then see how they all compare to each other. Does that make sense? Okay. All right. So that's kind of like where we left off, was this idea of how to tell very quickly if 2 fractions are equal, or if they're not equal, which one's bigger, which one's smaller. There's a beautiful shortcut, just cross multiply. Right? Almost too nice to believe. Okay. Yep. So if I want to make a general statement, a couple things based on what we just said, just to formalize what we just said. Given A over C and B over C are fractions. Now I just want to qualify this really quickly. What is the definition of fraction?
Pieces of something?
Okay, so that's a conceptual idea of what a fraction is.
Is it like a part of a whole?
Part of a whole, I like it. What could A be and what could C be? What kind of number could A be?
Smaller than C?
Smaller than C to be a true proper fraction, sure.
Whole number?
Whole numbers, there you go. So a fraction is a ratio of whole numbers where the bottom is not. What number can I not divide by?
0.
0. So fraction is a ratio of whole numbers where the bottom is not 0. So given that those two are actually fractions, then A over C is less than B over C if and only if A is less than B. And that's basically like the first problem we did. If the bottoms are the same, then comparing them is easy. But I just want to show you what the formalization looks like for that. That's one thing. Second thing. Given A over B and C over D are fractions, then, can't go up anymore, damn it. A over B is less than C over D if and only if AB is less than CD. And that's basically capturing the idea we used here. That's that second piece. So that's what it looks like formally. I have to cover my ass and put letters in to represent any possible number it could be. So what's true about B and D then?
They're not equal.
Oh, sure. They could be equal. It would still work. But what's definitely true about B and D? They can't be. What can you not divide by?
0.
0. So B and D cannot be 0. Okay. I like it. It goes to the room one and put a lot of emphasis. Okay. So now we're gonna get into some nifty stuff. If I ask you, there was a problem on that first fractions worksheet. If I gave you 5/13 and 6/13, and I asked you to find a fraction in between those two. If it was 5/13 and 7/13, please, dear God, Jeff, why didn't you say that? Because then it would be easy, yes? Well, what's the one little trick I could do for any two fractions that have the same bottom? If I need to, what can I do?
Multiply by 2.
Double them. Or triple them, or it doesn't really matter, to be honest. But one way to find a fraction between those two is I can make this become what? 10 over 26. 12 over 26. So then what's a fraction between those two? 11 over 26.
Yay.
So then if I had 10, if I wanted to find a fraction between these two, I could just keep going, couldn't I? Yes?
Do you have a problem as well, like if you got 11/13, that wouldn't work?
That would definitely not work because 11/13, how does 11/13 compare to those two things?
Oh.
It's bigger than both of them,
Oh,
right?
okay.
So it's a quick way to tell. But here's the main thing. I can't, as much as students want to, you can't take the problem you're given and change it into something else, right? So I cannot change this from 5/13. But if I write 10 over 26, that's the same thing. Because that factor of 2 would cancel back out. Who's got their calculator out? Anybody? What's 5 divided by 13?
5/13.
Oh, what? Oh, yours is stuck in fraction mode? Okay, at some point I want to show you how to change it.
0.38.
0.3. Blah, 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 right? What's 10 divided by 26?
Same.
Of course it's the same thing. Okay, good. So listen, if I ask you, how do you tell a student that this is correct? That would be a good first step. Show them it actually comes out to be the same number. That's not good enough to explain why, right? So later today we're going to get a little bit deeper into why those are the same. On one level it's computational. If I rewrite this as 5 times 2 and this is 13 times 2, then the times 2 cancels because it's division in the middle. So of course they cancel. But that's still not good enough. I want a more basic concept as to why that's true. So we're going to get there. Okay. So what if I gave you a worse problem? I want to find a fraction between, 31/47 and 35/48. So let me just prep you guys, okay? I'm about to show you a derivation about a really kick-ass thing that, to be really honest, I don't think I ever knew until I first taught this class. So I'm going to show you a derivation of something, and then you can just use the results. You guys with me? This is going to happen. This has happened to us already. I show you, I prove to you why something works, and then we just use it. Yes? So I want to show you why. In fact, let me just show you the results. You can always find a fraction between any two given fractions, and I need you to understand. Is this problem asking you to add those fractions? Did I say anywhere that I want you to add those fractions? So what I'm about to do, I am not adding the fractions. Well, one way, if the problem says find a fraction between these two, something that will always work is if you just add the tops and you add the bottoms. If I do that, I get 66 over 95. Now, is anyone curious as to why the shit that works? Me too, good, all right. It's easy as shit, it's awesome. But I would hope that when I show you this, you go, that's cool, but then why? Okay, good. Let's just double check real quick. Help me out, calculator people. What's 31 divided by 47? Any calculator people?
0.659.
Thank you, go up 3 places, I love it. What's 35 divided by 48?
0.729.
729? Neat. And what's 66 divided by 95?
0.694.
694. Is that between this and this? So that fraction is between this fraction and that fraction, yes? Now obviously when you're first teaching students fractions, you're not going to use decimals to explain shit because you haven't gotten to decimals yet. But for you guys, we can talk about decimals because you all know. Okay. You guys sit by with me? When will that work? Always. So if I go back to the problem we just did a minute ago, which is where, Jeff? If I just add those together, this is really interesting. If I add those together, what do you get? 5 plus, I'm sorry, let me be really careful. I'm not going to add those fractions. Add the tops you get, add the bottoms you get.
26.
So if they have the same denominator, it actually comes out to be what you would get if you did it the way we did it. You guys with me? This one, do they have the same denominator? So it's not going to work that way, but still, it gives you a fraction that's in the middle. So let me show you why. This is going to be very exciting. So everybody just proofs, I know. They just, everybody go, oh, it's proof. Okay. Everybody's just really going. So, do y'all agree with me that this one was smaller than that one? If I want to find a fraction between two given fractions, what's the one thing that can't be true? They can't be the same fraction. Does that make sense? If somebody says, give me a fraction between 3/4 and 3/4, I'm like, you have given me no room. Yes? Okay. So given, oh my God. A over B and C over D. I like that reaction. Hold on. Can't let that stand. Yeah. Good job, Jeff. You wrote. All right. It's a big deal for me, okay? Given A over B and C over D, where, okay, that I'm just kidding. A over B is less than C over D. So there does exist at least one fraction between the two of them. In fact, do you guys remember how many fractions are between those two? Infinite number. Because I can keep doing that thing we did in the first place forever. Let's not do that, okay? Again, this is weird. Proofs are weird. They're not the most obvious things. You're never gonna have to do this yourself, okay? But just watch. Doesn't this mean that AD is less than BC? Is that cool? That's a thing we used earlier, yeah? Let me make sure that it says less than. There you go, Jeff. You guys with me? All right, I'm about to do a very proofy thing. I'm gonna do a very proofy thing. I'm gonna bring something in from out of nowhere. I'm gonna make sure I'm gonna bring the right thing in from out of nowhere. There it is. Okay. What did I just do? What have I done?
You had the.
What did I add to both sides of this true statement? AB. So is this also a true statement?
Yeah.
Yes, we talked about that before. If I have the same thing to both sides of an inequality, then inequality is still true. Nothing amazing. Can you factor this side? What comes out of this side? What do they have in common? A. and there'd be b plus d. Is that cool? Just putting in alphabetical order, just because. And of course, this side I can take out a b, and alphabetical order, just because. If I divide by b and I divide by b plus d, I get this part, yes? So just to truncate this a little bit, because I can sense people going, oh, just not good. Okay. My claim is that if I wanted to find a fraction between those two, I could just add the tops and add the bottoms, right? And that would be between a over b and c over d. Do you guys see how I got this part here? You guys see how I got this part here? This part here? Yes? Okay. I could do all of this again, and I won't. I could do all of this again and get this part. I can do all the same work. I just add a different thing here and make this, and I get the same expression. So that proves that this is true. So we proved, let me bring out the cat. We proved this part. I could do this whole thing again and prove this part, in which case this whole thing would be true. So now we can just use the results. If I give you two fractions, and I just say find any fraction between these two. So I give you 11/19, and what else, Jeff? I don't know, Jeff. 19/22. And I say find a fraction between those two. How would you do it? Add them, yeah. And be careful. We gotta be careful when we say this. I'm not really adding the fractions. I'm doing something which is completely illegal if I was actually supposed to do any math to these. I'm doing a process that finds a number between those two, finds a fraction. So, dear God, this might be why I was never shown this when I was younger, because that gets trippy. Then students start to think, oh, that's how you add fractions. But so what would a fraction be between these two? 30. Use compensation. So 20 plus 21. 40, right? I can steal a 1 from 22 and get a nice round 20. Does anybody ever, you don't have to say, but is anybody using some of the stuff we've talked about at any point in your lives? You know, like, I refuse to, Jeff. I make a point not to. Yes?
There were some third graders that were trying to do like area with the rectangles, and they couldn't figure out what 40 times 37 was. I said, okay, well, you can do 40 times 30 and then 40 times 7.
Kick ass. I love that. Yeah, one of my students a while back, it was in my geometry class, and he said his job was like redoing the insides of cars, you know, like reupholstering the insides of cars, and he would always overestimate, and he said, you know, then he started to realize the shapes of things, and he said, I was wasting less product, so he's making his business more efficient. I'm like, okay. Yes, good, all right. So, let's watch little people doing some math. Dear God, Jeff, shut up. Okay, I will. Oh, I forgot, did I log in? No, I didn't, of course not. Why would I? Oh, is the grades up here? No, thank God.
Did you pass back all of the homework that you had?
Oh yeah, all the homework I've graded so far?
Oh, okay.
Hell yeah. You gotta mean it, you gotta mean it. You gotta mean it, you gotta really be there.
Because you have to turn it all the way, push it in, and then pull it.
Yeah, the doors are picky. Alright, let me see. Okay, let me stop recording so I don't get copyright strike. In terms of the fact that they're just a way to represent an idea, number versus numeral, that kind of thing. So now, of course, that we've identified fractions are numerical quantities, just like whole numbers are. We're gonna start doing stuff that doesn't like adding, subtracting, multiplying, dividing, right? So if I wanna add two fractions, how could I do, for example, if I'm gonna add 1/5 plus 3/5? Can you guys come up with a way, take a minute, come up with a way to do that visually? What's a visual way you could do 1/5 plus 3/5? Like a geometric kind of approach. Region model kind of thing. Okay. So what did you guys do? Anybody? Yeah.
Similar to the hexagon thing, I drew pentagons, and so I kind of divvied it up into 5 little chunks.
So you mean, did you draw a circle and cut it into 5 parts? Or did you draw?
No, I literally, you said geometric, and I'm like, okay, pentagon, here we go, so.
Alright, so you drew a pentagon.
Yeah.
Okay. And then you broke that up into
5 triangles.
5 parts, yeah, okay. Let's see if I could do this on the fly. Not really. Too bad, Jeff.
It's a point at the bottom.
Yes. Okay.
Upside down house is what I learned.
Yeah, good, yeah, exactly. And then you've got like little parts to it, telling you those are equal. And so what do you do with that then?
I shaded in one of the.
Shaded in
triangles,
one of them, so that's the 1/5.
And then I added, or did another upside down.
Another
house.
one, okay, yes. So not exactly a house, but sort of a house. Yeah, that'll be fun. And then I got my triangles. So then you put shaded 3 of them, okay? And then, so you can actually, you can think of it as like detaching these. So you got 3 triangles that's shaded in, and then you can just put these 3 into that one. So it ends up, of course, with, let's all suffer with Jeff drawing another thingamajig, and then you would end up with, of course, 4 of those bad boys. Okay, I like it. Does anybody else use a different shape?
Use a rectangle.
Rectangle is a good option. I like it. Much easier for non-artistic Jeff up here. 1/5. You're good. You're good. 3/5, and then you could do something very similar. You could just sort of say that you're picking them up and putting them in. So then you end up with 4/5. I like it. I like it. So region models obviously are excellent first things to go to really let the student build on the most basic understanding of counting objects. Now, let me ask you this. What about if I wanted to do, one other thing, before we leave this, what about a measurement model? What does that most fundamentally mean, measurement model? Number line. How would you represent 1/5 on a number line? What would you do?
Like
0?
0, just doing it as a fraction instead of like.
What would this be then? 1. And then you just make crazy stuff. So you cut, how many cuts? 4. 1/5, 2/5, red 5th, blue 5th. Okay. I like it. We're talking about 5ths, because then I used to feel like I have a lisp. One of the most evil things in the world is that we gave it the word lisp. So then how do I represent 1/5 plus 3/5?
Start at 1.
Same way we did 1 plus 2 back in the day, right? 1/5 plus 1 to 3/5 is 4/5. So, okay. So measurement model's kind of nice. We talked last time about how you can break up 0 to 1 into parts. Okay, I like it. Okay. So how would you do the same idea with this? Take a minute and figure it out. Do a region model first. How would you represent that using a region model?
Like draw a picture.
Oh, do it, and then we'll talk about it. Yeah, I'm sorry, yes, draw a picture. Region model. Geometry. Geometry. Bless you. Probably didn't. Okay. So of course now we have a situation where the drawings you make, the parts won't be the same size, which will kind of suck. So I'm just going to use a rectangle. That's okay. So there's 1/2. I have the same rectangle. It's 1/2, and there's 1/4. So this is really almost too good to believe, because I understand a lot of this in here. Trust me, some of my students in my 281 class, Calculus 3, they don't like fractions. So it has nothing to do with your overall level of ability with mathematics. Fractions just trouble humans. Where did you guys, where'd you go from here? Somebody I haven't heard from yet. Sorry, let me, did anybody do something from here? Yes. Sorry, brother.
I just did the circle, so half of a circle.
Oh, so you did circles, okay.
Yeah,
So you did circle, you did half of it like that?
yeah, and shading one side.
And then you
the
have-
circle, now 4 parts and shading one side. And then, full circle, and then I added a half, and then just like 1/4.
Oh, so you did this kind of thing,
Yes,
right?
yes.
But then what would that be?
You could like, do like a little dotted line to show like, oh, so you could still split it
Shout.
into like 4 parts.
Yes. Okay. So I like it. You literally took this half and shoved it next to, yeah, go, there we go. This 4th. And then of course, if you did that with a young human, they'd say, oh, shit's that. But then if you break this up, you're like, oh good, there's 1, 2, 3/4. So one thing you could do is just from the beginning, very first thing, do this. What does that represent? That represents 1/2 equals 2/4, exactly. So that's another way to show building fractions up, right? So down here in my little model, if I just cut this up, each part in half, now I've got 2/4 and I've got 1/4, and if I take this out, it fits perfectly there. So then I end up, of course, with 3/4. Okay, I love it. Yes. That naturally is the idea of LCD. So creating an LCD is literally taking a fraction and cutting it up into more parts. So in this case, I only had to take one fraction. If I took half of this, if I cut everything in half in that picture, that made it 4ths. And then it was immediately like terms with the 1/4. So what if I had, for example, what did I use? Yeah, let's just do that. That makes it nice. 1/3 plus 1/2. So this will be, let's just all use rectangles. Go ahead and try to set that up. Do that. Oh, okay. Oh, okay, good. And then I can do that. Kick-ass. So let me catch up to you guys. So I got 1/3 and 1/2. Now, if you cut either fraction up into subparts, they'll never match. If you only cut one of the two fractions up into parts, right? But obviously, if you cut, well, maybe not obviously, to a little person, but for all of us, we kind of see where this is going. How many parts do we want to cut the 1/2 in? Yeah, I want to end up with 6 cuts, so I want to cut each piece of the half into thirds, yes? So I'm literally taking 1/3 of 1/2. Does that make sense? Ish?
Yeah.
Okay. Do you see how I just took, I should really do that in different color, that would be smart. I'm not a very smart man, Jenny. Oh my God. What am I, oh, I'm undoing what I did up there. There it is. There we go, okay. So let me do this in different color. So if I take the thing that represents 1/2 and I cut each half into 3 parts. Now it's out of 6. Now what are you going to chop this up into? Each part I'm going to cut into halves. Yeah, I'm going to cut it into 2 parts. So now this represents what? 2/6, and this represents 3/6. And now I can add them. I could take these out, and I can plop them into these spots, and I'm going to end up with, holy shit. Okay, I like it. So this is the idea. When I'm building fractions up, I am literally actually chopping them into more parts. That's what we're actually doing. So of course, if 1 out of 3, that's 2 out of 6. If the brownies, if I chop something in 3 parts, then 1 chunk of it is 1/3 of it. If I chop each one of those in half, but take 1/3 of it, that's actually 2/6 of it. So as I subdivide, the top and the bottom grow. And okay, kind of funky. Obviously, we're not going to do visual representation for something like 1/12 plus 1/15. You guys with me? I'm not going to make you do that. This is not quite that evil yet. Give me a little bit longer. I said that 10 years ago. I said 10 years ago, I said, check in with me 10 years from now. Some of you guys are like, you hated it. So, what about, real quick, what did we just do? We did 1/3 and 1/2. What about this? What about 1/6 and 1/4? Okay. So just to kind of go through this a little quickly. 2, 3, 4, 5. Yeah, that's not bad. That's horrible, Jeff. Can't abide. Can't let that stand. Jeff, you keep hitting the redo button. What is happening? There you go. Okay. Let me try this one more time. 1, 2, 3, 4. That's a little better. No, it's not. Yes, it is. 1, 2, 3, 4. And then 1/4, about the same size. 1, 2, 3. Okay. So 1/6, 1/4. Now, what point do you think I'm trying to make here? Because over here, we broke this up into 3 parts, and we broke this up into 2 parts. Do I have to break this up into 4 parts? No. So I want to have the same size slices in the end. I don't have to make them both 24, right? How do I make them the same size slice? I can cut the 1/4 in thirds, and I can cut the 1/6 in half. So it still gets a little bit tricky, but, oh, let me do this different color, Jeff. Jeff learns and then he forgets. Oh, this is exciting. Okay. So now this will be 2 12s. And then if I cut this one in thirds, oh my God, nobody will be seated during. Oh my God. My brownie pan got big there at the end. Now this represents how much? 3/12, yes. So then 2/12 plus 3/12 is 5/12. What's important, and this is obviously why you might want to use computer-generated graphics instead of handwriting, unless you're a really good artist. Basically the opposite of me. is that the area you cover is the same. You're just cutting it up into more parts. So that's why it fundamentally means the same thing. Okay. Alright. Okay, so getting to the purely mathematical way to do this. No, it's not. Go away. So what if I have 4/15 plus 5/12? Does anyone remember LCD? We call it LCD because the numbers are in the denominator, but what is LCD really? LCM, kick-ass. So all the approaches we use for LCM could come into play here. So what do I really want to find? I want to find the LCM of 15 and 12, kick-ass. Now, I will tell you, remember all the approaches there were to finding the LCM? You guys remember that? There was a set method, there was the prime factorization, blah, 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 right? The absolute best way is one that we talked a little bit about, is called the build-up method. And what I start with is, what is the GCF of 12 and 15? 2, 1, beat them. So break up 15 in terms, so does everybody agree that the GCF is 3? What's 15 minus 12? 3. So the GCF could only be some factor of 3. So thankfully 3 works, or else it'd be nothing. What's 15? 3 times 5. And what's 12? 3 times 4. I could prime factor 12 further, correct? But that's not the point of what I'm doing. I'm not prime factoring it. I'm factoring in a way where I recognize what they both already have, and then there's another part that they don't share. So I think I gave this example before about the ice cream. No? I haven't given the ice cream example? Okay. Does anybody have kids? Anybody ever been around kids? Anybody been around kids that got ice cream? Anybody ever been around kids where one kid got sprinkles and the other kid didn't? Okay, remember? Okay, good. So yeah, so they both have ice cream, that's the 3. They both have ice cream. This kid got sprinkles and this kid got marshmallows. They're both upset for different reasons, correct? I don't want to have marshmallows. I got sprinkles. So then you're going to give the one kid sprinkles and the other kid marshmallows. You're going to give each one what the other one has that they're missing, correct? Okay. Jeff, you can barely handle. I'm going to go for a third color. Everybody stand up. So what is this first dude missing that the second guy has? What is the first dude missing that the second guy has? 4. So multiply top and bottom by 4. Plus the second dude missing is the first guy has. 5. Multiply top and bottom by 5. So what's the bottom now? What's 4 times 5? Yeah, 20 times 3? 60. So I get 16 60ths, yes? Plus 25 60ths, and now it's just like terms. If I have 16 things plus 25 things, I have 41 things. Yeah. Okay. Chum, 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 chum. Feel pretty good that doesn't reduce. So that, to me, that's how I show, back in the day when we were allowed to teach Math 80, which was where we literally taught people what 2 minus 7 was. Because some people get to this level and they don't know what that is. So that's, we used to be able to teach that. We're so far past that now, we don't teach that at all. But this is how I show when we get to fractions. This is, to me, this is the best way to figure out when the numbers are weird on the bottom. If it's 3 and 6, screw it, I don't need this, correct? You can see it's missing a 2. Okay. Let me see. Yeah, last couple things. And then I'll let you guys work on a handout. Every time we learn a new number type, or new operations or whatever, we have to talk about properties. So, are fractions closed under addition? What the hell does closed mean again? Yeah, if you take two fractions and add them, you have to end up with a, and well, in this case, you have to end up with a fraction. Because what's in your room? Fractions. So is there ever a case where you can take two fractions, add them, and you end up with something that's not a fraction? Now, I understand why you guys are saying yes, because what's, for example, 1/4 plus 3/4? Isn't that 4/4? Or even better, isn't 1 1/1? And what's the definition of a fraction? Any ratio of whole numbers. So 1 is a fraction. 1/1. Any whole number is a fraction, because what can you put on the bottom? 1. So are fractions close? Yes. What about, and to be honest, I'm not sure what the book says about that. I'll have to take a look. It might say no, because they get whole numbers, but they're fractions, because they're ratios of whole numbers. They'll look that up. What about commutativity? It's not, by the way, it's not commutativity. We're not going to build a commune and live together. Commutativity, like you commute to work. What do you guys think? Would commutativity work? If A is A over B plus C over D, is that the same thing as C over D plus A over B? Why? Let me ask you a really horrible question. You ready? What's the LCD for this? It's not that horrible, to be honest. BD. Isn't this first guy missing a D? Isn't this second guy missing a B? Is everybody with me? But what's this then? Isn't this CB plus AD over DD? Or let me even make it more, stick with it, we're almost there. DB, there we go. Wait, is that weird? There we go, Jeff. I did something weird. Are these the same? Yes, they are. Because what do we already know? We know that whole numbers are commutative. Aren't these whole numbers? So fractions are commutative because they inherit the property of commutativity from their whole numbers. They're just ratios of whole numbers, and whole numbers are commutative. So how do you feel about associativity? You think fractions would be associative? Yeah, they inherit again, right? A plus B, A over B plus C over B, blah, blah, blah. It would all become, the tops would become the same numbers, just with parentheses in the different places. It inherits it from whole numbers. Once you get an LCD, the tops are whole numbers. You can just inherit all the properties. Does that make any sense? Since fractions are built from whole numbers, I can just inherit all the properties from whole numbers. So of course you got additive identity. What's the additive identity for fractions? What's the additive identity for whole numbers?
Zero.
Because that's the number you add to maintain something's identity, correct? Is 0. So what is it for fractions? 0 over 1. You guys kind of with me? If I add 0 over 1 to any, or in fact, 0 over who cares? What do I add to 1/3 to make it stay the same? 0 over 3. Is that cool? Does that make sense? Okay, so the properties are not that big of a deal. All the properties are still there because we sort of inherit it, because the tops are made out of whole numbers, so we sort of inherit that from them. Okay, so let me do this. Before I give you the worksheet, I'm gonna, oh man, I keep adding strokes, it sounds terrible. I want you guys, let me see, well, how many people do I have? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. You're gonna play along, yeah? Okay. I need to get my, shoot. So let me do this. I'm gonna group you guys up. Questions just that not in the same order? Okay, so let's see if we can all handle that. Now, some of you guys got to be spiders, candy corn, but only a few of you could be purpose. So, I'm very sorry that only 3 of you could be. Sorry. The broom team really enjoyed being a broom. So, number 1 we talked about already. We talked about this before. Are there any fractions that are also whole numbers? And all it takes to be a fraction is to be a division of two whole numbers, where the bottom is not zero. That's all it takes to be a fraction, yes? So can somebody give me one fraction that's also a whole number? 3/3. Kick ass. Why is that a fraction? Because it's a ratio of whole numbers. Why is it a whole number? Because it's freaking 1. Alright, so could you describe every fraction that becomes a whole number somehow?
Yeah. Any fraction that the denominator divides equally into the numerator.
Beautiful. So if the denominator goes into the top evenly, then that would become a whole number. Okay. Oh wait, okay, beautiful. Yes, put those back over there. What about, now this was the one where you guys didn't show me, this is the one we did together. And we got the Millennium Falcon. Or not, if you don't like that, sorry. This one, I think everybody showed me, so I'm not gonna do it again. Everybody kinda showed me, so you guys all saw how to do this. If I had parts that broke down into more parts, we could do more complicated problems physically. And hopefully whatever school you end up at, don't count on the budget being great. So you might be constructing some of your own stuff, depending. Okay. This one I appreciate. Some of you guys did this in different ways. Can somebody give me one way that you did this problem? Whichever number it was.
I just the other one by 23.
Yeah, so some of you guys made the bottoms the same, which makes the whole problem easier. What were the fractions you got?
184, 345, and 285, 345.
And now you can just pick anything between the two, right? Because I just said find any fraction between. So what did you guys pick?
193.
Shadow! Did anyone do it differently? Yes.
I just added the numerators together in the denominators.
Yeah, so you could do 8 plus 19 over 15 plus 23, and you got
27 over 38.
27 over 38. Okay. I like it. Anybody do it differently? I can't think of another way to do it. I just wanted to see. Okay. What about this one? Now this one I made it kind of rough, kind of easy because they have the same denominator. I could reduce this one, couldn't I? But why would you? What do you actually want to do? Yes.
Multiply each one by 2.
Yeah. So this would become
16.
16 30ths, and this would become
18.
18 30ths, so then you'll get
17 30th.
17 30ths. Now, real quick. Let me see if you guys are cool with this. You ready? I'm going to create a number that's not a fraction, but then I'm going to make it a fraction. Because I'm weird. What's right between 8 and 9? Here's this spider. Get it. What's right between, good lord, I'm zoomed in. What's right in between 8 and 9? You can do it.
8.5.
8.5. Is that a fraction? Why not? It's not a whole number. Good. So how to make it a whole number? I can multiply by 2, yes? That's 17 over 30. Same answer you guys got then. Anyway, so that's just a side note. So I can do it that way if I want to. Find a number in between the tops and then just multiply and make it a whole number so it becomes a fraction. It's good for you, math. Okay. Somebody had a really good question. They said, does PEMDAS still apply to fractions? And PEMDAS applies to numbers. Fractions are numbers, so PEMDAS still applies. Right? So PEMDAS is the underlying grammar of mathematics, which is why it sucks. If you've ever learned a foreign language, right? Like I did, because math was my first language. If you ever learn a foreign language, it's the grammar that often sucks. The vocabulary is just memorization, but the grammar is like, holy shit, what's wrong with you people? Okay. That's what a lot of people think about English. English is one of the hardest languages to learn second on the face of the earth. And some of you guys know that all too well. And I'm sorry, I wasn't around when they made it. So the first thing I have to do on this is, what do I have to do first here?
Times 5.
So I have to do the inside first.
Times the 5.
Kick ass. So I want to make a common denominator, so I'm going to multiply this by 2. So we get 7, 6 plus
9 over
9 over 4. Unfortunately, neither one of those reduced. That's what you always kind of look for first, so you can kind of reduce your numbers, but that sucks. None of them reduces. Damn it! So let me see if you guys remember this. Here's another way to do LCD. We've already got several ways, correct? Whatever way you like best. What's 6 times 4? Holy shit, is that the LCD? No. What's the GCF of 6 and 4? 2. What's 24 divided by 2? That's the LCD. If you multiply them, I don't know if anybody remembers this, we actually talked about this. If you multiply two numbers and divide by the GCF, you get the LCM. That was a little theorem we had before. Somebody remember that? Okay. A little theorem if you remember. Okay. This is another way to get the LCD is 6 times 4 is 24. They have 2 in common. Divided by 2 is 12. So then this would become who to what? 14 twelfths plus 27 twelfths, and you get 41 twelfths. 41 just likes to show up today. Okay. And then finally, this guy was relatively easy, yes? Because what do you do to make this? You don't have to multiply, or you could. That's not too bad either. But what could you do just directly? Yeah, okay, I could cross multiply, and what do I get? 35 times 2, 70. 5 times 12. Which way do you put the inequality? So you put it the same way there. As long as this goes here, and this goes here, the inequality symbol remains the same. Did anybody do that a different way? It's okay if you didn't.
I just did 5 times 7.
Yeah, if you change 2/5 to be times 7 times 7, then you can see, Jeff, that's a 34. Then you can see that first one's bigger because there's 14 of them, not 12 of them. So either one of those take about the same amount of time, so I don't care which way you do it. So if I don't say to do something a certain way, you can do it any of the ways that we talked about. Okay. This guy, you could spend some time reducing this, whatever, but it's easier. You got a calculator. You might as well just do what? Round both lines. So what's 870 times 18? 15,000? 660?
Yeah.
Neato. And what's 45 times 348? Same thing? Oh, look at past Jeff. Okay, so then this is equal. So if you reduce until you go insane, both fractions become the same number. Yeah.
Were you supposed to change the improper fraction to a mixed number?
For which part?
Number
The last
4.
one.
Oh, I'm sorry, I forgot, yeah. Look at me, I'm a horrible student. Put answer into mixed number notation. How do I change this into mixed number notation? There's a really cool way to do it if you don't like division. I showed you how to do this. What number below 41 do you wish was up here? That's easy to divide by 12. What number below 41? 36. 36 plus what is 41?
500.
Holy shit. What's 36 divided by 12? What's 5 divided by 12? I don't know. Done. That's much easier than dividing. Or if you divide 12 goes into 41 3 times. 3 times 12 is 36. Subtract, you have 5. So you get 3 and 5 plus. Right? How do you change improper fraction to a mixed number? You divide. Or you could do this neat thing. You literally do the part you can and you leave the part you can't. That's all a mixed number is. Okay. I love you guys. I'm going to let you out early, especially my brooms. Sorry, brooms. Let's stop it. I'll take back my stuff, put them all back in the bag. Homework from like the test. That homework I'll grade as I can. And normally I grade the people that made lower grades first. Stay. What'd you think?
Yeah. It was the
Oh, yeah. That stuff is easy to forget because once you get to the level, what's really weird is you never talk about it for a while, and then you get high enough up, it dominates your life. Because then you start talking about, what if it wasn't the number system? What if it was a different number system? Would it still be commuted? And then they come back with a vengeance. So for the longest time, you don't talk about it at all, yeah.
Yeah.
It's funky.